And our first talk today will be by Klaus Birken. He works as a language engineering, model systems engineering person, expert guy at Itemis. And he's going to talk about Simbench, a model-based tool for analyzing system resources and timing and stuff like that. Welcome, Klaus.
Hello.
Take it away.
Okay, so hello everybody. Thanks, Marcus, for the introduction. I'm glad to be here. I just made it, I think, on the last day, so last chance. Okay, I will talk about interactive model-based resource analysis for systems engineers. So let's pretend we are systems engineers and want to create some great new technical product. And we will tackle the challenges we have as system engineers here. And we build an MPS-based tool for this, and this is what I will show today. So this is the agenda of the next hour. So first of all, I will give some motivation and show you the challenge of the systems engineer. And then we will look a little bit into the theory. How does the simulation work? And I will motivate why we want to have a spreadsheet-like user experience. Spreadsheet only in one way, not in the commonly thought of way. Then I will give you some background on our implementation. What are the ingredients there? Then we look at the tool. I will give a demo. Then a little bit behind the scenes section, and then a short wrap up. Okay, let's dive into it. Let's start with the systems engineers challenge. And as you all know, today's technical products are often embedded systems with lots of software. They are very feature rich and due to this increasingly complex. And in addition to this, the cost per unit for the hardware is often limiting so that we don't have much headroom for developing our software. So the question arises, and this is one of the main challenges. So we will build software components which run on this embedded hardware and will use the resources of the embedded hardware. And will the hardware design be sufficient for all the software use cases? Will we have enough memory, enough compute power, and so on? So there are lots of resources which we have to look at. The problem is even worse because in some markets like automotive, we have especially high volumes, and this demands even more or smaller per unit cost, because you can save every euro, every dollar with each of these devices, and if you build 1 million of them, then it matters if you can save 1 cent. Yeah? And this again reduces the available hardware resources and intensifies our challenge. Now, the traditional approach would be you build some prototypes, so you have some hardware sample and implement some software and run it, and then do some measurements, and then you find out, okay, it will not work. So what will you do then? Usually, this is too late. It would induce a big pile of costs and additional development work. And so what we want to do is front loading. We want to do it early in the process. So basically, we want to build a model of our system and then execute the model. So simulate the model. And this will allow us to evaluate architecture decisions very early in the process. We can validate timing requirements without implementing everything. And we can also find design flaws and fix them. And even during the development, we can find optimizations and test them on the simulator. When we have the model and do the simulation and come back to the model again, looking at the results, this is usually a very fast cycle. So if you think about how the engineer works when building the real system, then this might take several minutes. You change your software, build it, link it, flash it on the target system, test it, do the measurements. So this is not a fast process. And by doing this in the simulation, you can do it in a few seconds, and if we are lucky, even immediately, and we will see how this works later. So what we aim at is an executable model with direct feedback. So now let's look into a little bit into how the simulation works. This is the theory part, but it's just 4 or 5 slides, so it will be done soon. So this is a very simple example. We are always talking about consumers and resources. So consumers consume resources while they are executing. And in this example, we see, to check that the mouse cursor is away. Okay. In this example, we can see the time from left to right and the consumer P, which needs 100 milliseconds of resource R. The resource might be a CPU or a network or some memory. Okay, so what happens? So if there's no other consumer on this resource, then it will take 100 milliseconds of wall clock time until the resource activity is finished. And so after 100 milliseconds wall clock time, the consumer can proceed and do the next thing. Let's make it slightly more complicated. So here our consumer P wants to access 3 different resources in parallel with 3 different amounts of resource action. So for R1, it uses 200 milliseconds. For R2, it uses 100, and R3, 300. And so as we can see, there's no other consumer. So after 300 milliseconds, the last resource will be consumed. So everything is done after this period of time, and it can continue with the next step. Let's look at a sharing example. So now we have 2 consumers for the first time, Q and P. Yeah, they are running on the same system and using the same resource R. Every of them wants to have 100 milliseconds. So in total, it will take 200 milliseconds wall clock time if every of both consumers gets 50% of the resource. And we are applying a very simple scheduling scheme here. So just give everybody the even share, and then we can compute this. A little bit more complicated, and then I think we are done for this. So now Q still needs 100 and P now needs 200. And what we get now is for the first 200 milliseconds, they have to share the resource until Q is satisfied. And then starting from 200 milliseconds, only P uses the resource. So it takes another 100 milliseconds and then everything is done. What you can see here is that this period, so this point in time at 200 milliseconds is introduced by this combination. And this is important because we can, with our simulator, can jump from the 0 point to the 200 point and then to the 300 point, because in between nothing happens. They are consuming, but this is not interesting for the simulator. So as you might have expected, we not only have 2 consumers, that would mean 2 processes on some system. Now we have many, and we also have many resources. And so we get coupling from consumers to resources, like, again, memory, network bandwidth, processors. So this means this is a whole graph of coupled entities. And there is one thing left I have to mention here. So when P and Q now work as they are expected to, then at one point in time, Q might need something from P, which is expressed as a logical dependency usually. And then Q has to wait until P has finished its step, and then Q can continue. And this is a typical thing for this kind of systems, that there are some dependencies which we also have to be able to model. Yeah, so I mentioned this already quite often. So the system is mostly in its steady state. So although the consumers are working and are doing something and also are using resources, nothing significantly changes in this period of time. the points in time where something changes is exactly at this points where some resource consumption ends and another one begins, and so on. And this is why we called our simulator warp, because it jumps from time step to time step. And if we are lucky, then even a complex system can be reduced to maybe a couple of hundred warps through time. And so the simulator can do its execution very quickly. So this is a special case of discrete event simulation, and typical applications of discrete event simulations are optimization of schedules, for example, in hospitals, production plants, or IT systems with servers and networks and tasks which are running, and also the resource consumption of embedded systems. And this is what we want to tackle here with the tool I will show today. So I already mentioned that this cycle of changing the model and looking at the results can be quite quick. And as we have seen just now, the simulator can be fast because it can warp through time from one point in time to another. So what if we avoid the generate build step at all and do this in an interactive way? And we know how such interactive tools are working by looking at the spreadsheet examples. So here we have a distinction between user content and computed content, which you can express by filling a formula in a cell. And then the user change leads to immediate updates. And this kind of liveness is what we want to achieve with the tool Simbench. Okay, now a couple of details about the implementation. So first of all, let's zoom out. This is the technology stack we are using here. So on the very bottom, obviously MPS. And then we have the usual extensions and embedder platform. And then on top of this, we are using IAT3 open source, especially the big kernel F part, together with the interpreter and the expression language. And then on top of this, we have IAT3 core, which has a couple of subcomponents which we are using here. So one is variability, one is components, component language, then the warp simulator, and the Simbench tooling itself. Now let's take a closer look on the warp Simbench part. So if you look at the left side of this diagram, you can see how we currently implemented it. So Simbench is a couple of DSLs, a couple of languages implemented in MPS. And warp is an external library, a jar file. Actually, xwarp is an open source engine which is available on GitHub. I put the link there, and it's we implemented it using Xtend, the Xtend language. So what we get there is a Java library which we can use here, and this mapping from the Simbench model to xwarp is done with plain Java code. So we didn't use a generator here or some model transformation. We just access the API of the simulator to be fast and to get it running in an interactive way. And on the other hand, we will get results from the simulation and we will lift them back into the model. Meanwhile, after we have built this solution on the left-hand side, we built this warp DSL, which is a low-level language which can be used to use warp directly. And so, as is indicated by the different levels of blue boxes, so the abstraction level of warp is much lower, and there's additional functionality in Simbench which we don't have in this warp DSL. But we have built this to be able to build customer-specific DSLs for systems engineering and to map them to warp. And we actually did this in customer projects. So Simbench doesn't apply a SysML standard, for example. So if a customer wants to model with SysML, we would build this and map it to Warp. Maybe losing this interactive property of what we have with Simbench. But yeah, we would choose the MPS generator framework, or we could use an incremental model transformation like shadow models, so that this the Warp DSL is available all the time, and then we can also implement this interactive user interaction. And this is what we will do in the future. So it's planned to also build a new Simbench based on the same principle. So using the Simbench models, transforming them with shadow models in an incremental way, and then doing this interactive mapping to the simulation engine. What we also use is product line variability, because if you invest a lot in such kind of executable models, you don't like to build a new model for every variant or every product instance. Instead, you want to build this 150% model, which can be applied to many of your products. And this is what we are doing here. I will not go into detail here, but this shows the idea. So we're using feature models and configurations for all kinds of product instances. In this case, the product is the executable model, which is built by the system engineer. Some more implementation aspects. So what Simbench uses is the hierarchical component language, which is provided by IETF3. In the screenshot, you can see the graphical projection using the graphical editor. We use this for modeling hardware and software architecture, and then there is a partitioning or deployment model which connects both. We are using kernel F for arithmetic and Boolean expressions, and we are using the interpreter of kernel F for evaluating these, and this has to be done during this interactive cycle, because we have to give something to the simulator and then we have to evaluate it first. I already mentioned the lifting of simulation results. So the simulator produces lots of results, and some are projected directly into the model and some are accumulated, and we can build some kind of Gantt charts from it. Here we are using J3 chart, which is somehow limited, but at least it's a nice demo. In real world tools, we have built other things which are not part of Simbench. Okay, now we are the tool demo is about to start. I want to give you an impression about the application domain for the example I'm using during the demo. But I think due to copyright issues, I'm not allowed to put some diagram or some picture of it here. But I think we can do a little questionnaire, so that this will be selected by chance, and I don't have any copyright issues. So I prepared 3 domain examples, and those have the ID M, P, and S. And when I now say go, you pick one of those letters and put it into the chat. And Markus then, hopefully, who will help me, will look at the first 5 of them and pick the one which has been put in the chat most. So if there are 3 Ps, then I will click on this domain example P. Yeah. So go.
All right, I'm watching the chat.
Did anybody put in a letter?
Yes, stuff is happening. Stuff is happening.
Uh-huh.
All right, we're at a tie. S wins.
S wins. Okay.
Yes,
I will
wins.
click.
I didn't quite understand this copyright thing and how your thing here helps with that, but as long as you're happy, I guess we're happy.
Okay. Yeah,
right.
let's click on it. Takes the time to open the link. Okay, so it's Audi. Yeah, I didn't want to take this picture and put it into the presentation because I'm not obliged to take an arbitrary picture and put it into this public presentation. But now we all choose together that we look at this Audi website. So this is the device which we want to build in our example. So it's an infotainment system with navigation system and phone connection, and it has nice graphics, and you can use it by touch screen or head-up display and so on. And yeah, this is a state-of-the-art infotainment system, and now we are pretending to be the systems engineer who wants to build this kind of system. Okay, I already mentioned, so the system will need some kind of graphics subsystem, and yeah, this is a part of our software model. And this software model consists of a hierarchy of functional components, and this is one of those components, the graphics component. And what we can do here with the Simbench tool is to add this sim section, and this section will specify what the component does in a certain use case. So our use case we are modeling here is the power up use case. So you get into the car, switch it on, and then the graphics component will run through this sequence of steps. We are not interested in the actual activity after the startup, because the startup is our critical scenario right now, and we'll look into it. And so what we have modeled here is that the first thing this component has to do is to read the image, the executable, from some flash memory. And this is the size of the executable, 0.8 megabytes. And then it has to do some computation, some initialization of 70 milliseconds here. And after this has been done, so both of these actions will run in parallel, the image loaded step is ready. Next, we will try to reach the available state. And in order to do this, we have to do some synchronization with the graphics hardware, which is basically polling and waiting for some interrupts or whatever, and some more computing. So these use statements specify the amount of compute time we need for this step. Yeah, and after those two steps, the graphics will be available, and something can be shown on the screen. Yeah. Now, our system contains of many components, so not only of this graphics, but maybe 50 other components. So I think in this example, it's about 30 to 35. In a real world system, you will have a couple of hundreds of components. Okay, but now we want to understand how this would work in real time. So let's put this on the right-hand side, and let's look at this item here. So what we see here is a overall system description where we specify the functional root, which is the root of our software tree, and one component in this tree will be this graphics component we see on this side. So what we can do now is activate the simulator. Now we can see that it's activated because we get this active simulation cell, which shows how long the simulation actually took and how many iterations, how many time warps we had during this. But let's look at the graphics component first. So what we can see now is the simulation results, which are projected into this model, and we can see that only after a little more than 1,000 milliseconds, so 1 second, the image loaded step is done. So the executable is there and can be run. And then it takes another 300 milliseconds until the system is up and running. yeah, why is this? So we can play around a little. So for example, let's pretend that we don't have to load the image. So I just comment this line, and what you see is that for reading, for executing 70 milliseconds of CPU time, we need nearly 700 milliseconds of wall clock time, which means there are about 10 components running in parallel. And this is clear because our system doesn't only consist of graphics, but it consists also of many other things which have to be started, like the connections to other systems, and also diagnostics and many things. So let's use this again, and you see I can do changes and see immediately what the results are, because now the simulator is in the active state, and as I'm used to with spreadsheets, I get immediate reactions from my system. And this is a really nice property, because now a system engineer can work with it and can do experiments and get live responses. So now let's try to achieve some goal here. What I also want to show here is this little Gantt chart here. The screen resolution is now much too small to see everything, but so that you can open up this resource load diagram on a second screen, and now you see the time on the x-axis, and you can find out, for example, here, yeah, exactly 10 components are active in the early phase, and one of those components, the second one, is our graphics image loaded step. Yeah. And you can also see the flash activity. So 3 components are in parallel loading data from this flash memory. Now we can think about optimization things. So, but first of all, let's get the requirements right. And yeah, as I already mentioned, we are looking at the startup scenario, and this is specified here. Yeah, the basic startup scenario. And if I jump there, you can see that the scenario is just a collection of use cases. So in our case, it's just one use case, which is system startup, but I could add other use cases like low battery or compute a long navigation route and things like that. So you can combine use cases arbitrarily to execute other scenarios. And this is very useful, because by combining these, so you build each use case separately, but then you can combine them in a declarative way. And what we see here now is a list of semi-formal requirements. So the thing is, if you build a system like this, you will get tons of requirements, and only a certain percentage will be related to system aspects like timing, performance, and so on. And the systems engineer has to get these and then make sure that they will all work out, that they will be all satisfied. And what he can do now is to put them into the tool in a semi-formal way, so that the tool can check against the simulation results if the requirements are fulfilled or not. And one of the requirements is this one, which refers to our graphics available step. So you can see here, this is graphics available. This is mentioned here, and the requirement says the milestone graphics available shall be reached until 1200 milliseconds. And this is because we want to show a splash screen, and if you sit into the car and then turn the key, you want to see the splash screen immediately, but not later than 1.2 seconds. And there are actually legal requirements, not for the splash screen, but for other things, which have to be fulfilled in different countries. And what we can see here is this requirement is not met by our system. So we have to optimize it by 105 milliseconds, and then we are right at the maximum which is allowed. But we can try to do this. So what could we do? So one thing is we could convince the customer that this requirement is too restrictive, and we could tell him, oh, why not choose 1.5 seconds? Obviously, this will now the requirement is matched because we made the requirement less aggressive. But I can tell you this can be done only in a very small percentage of cases. So let's go back to 1200 and look at the implementation, which is currently our model. So what could we do? So one thing is we could talk to the developers and tell them, see, 70 milliseconds is too slow. You have to be able to do it in 50. And then we can see, okay, it's green. Because now we are below 1200. But the developer will say, well, I cannot do this. It's too complex code, or it's safety critical. I will not change anything. So let's look for something else. So maybe we can achieve some optimizations in the executable image, and maybe they forgot to remove the debug information, and then we can say, okay, we can optimize this 1.6. But we can see it's still not enough. We didn't achieve the 1200. So let's forget about this. And now let's look at a third optimization, which is maybe a little bit more interesting. And this is the following. So if we are looking at this Gantt chart we did before, we saw there are 10 components running in parallel. And maybe for some of the components, it's not even necessary to run this early. So we could introduce an artificial dependency to remove them from the early phase so that the graphics driver will get more CPU power. And let's do this. I prepared this a little bit. Let me find it. So here we have some navigation engine component, which is not really, well, it's the map. So we could argue the navigation map, which is the component which shows the map, it cannot do anything without the graphics. So why start it before the graphics is even available? And so what we could do is introduce some precondition, which says, don't start this step before graphics or unless graphics is available. And now if I put it into the model, you can see that the starting point of navigation will be worse, but we now meet the requirement. And this is a typical kind of optimization which engineers find with this tool, doing this testing. And if you want to do it in a real software, then you somehow have to build in the dependency from graphics driver to navigation, which might be hard to do just for experimental reasons. So if you here you can at least try in advance if it makes sense to do this. Okay, so this was the little playing around and showing how the tool can be used. Now let's look briefly at the variability part of it. So here we want to be able to model a whole family of products and not just the one we're looking at. And this also can be done by building or by providing these feature models. And one thing we could switch here might be the mapping from consumers to processors. So for example, the HMI component currently, so let's look at the HMI component that you can see the timing here. Okay, so you can see this is the the human machine interface, which shows all the buttons and the menus and which handles the joystick or touch screen and all this stuff. And you can see, so it's very slow. So only after 9 seconds you can interact with your system in the car. So you paid thousands of euros for this nice system, and you have to wait 9 seconds. So 20 years ago, you just switched it on and the radio started playing, and here it's different. Okay, so we want to optimize this, and in order to test different optimization possibilities, we could, for example, assume we have a second CPU, and so here we have two mappings. So one mapping says, okay, the HMI is mapped on the main CPU, or the HMI is mapped on the secondary CPU. And now let's switch it on by switching on the additional CPU feature. So this is a presence condition and can be used to do changes in the model. Now I have to find the configuration. So here we have the configuration where we can simply pick some features. And as you see here, this optimization additional CPU is not active right now. And now let me activate it. And now you can see by putting the HMI process on a different CPU, we are 5 seconds faster. We have to look into the details here, but so this would be a typical use case for using this interactivity. We just assume additional CPU, and then we can test what the impact would be. As I mentioned, every cent counts, so it's probably too expensive. But if there's no other way to satisfy all the requirements, then this will be a final step which will be done. Okay, one thing I didn't mention before, and this is the last thing I will show during the demo, is the reality check. So how do we know that the simulation does exactly what the real system will do? And this is especially important when there are actually real systems. So in this early phase, when the system engineer starts with his work, there's no real world thing which can be compared to. But later on, we want to know, there is an early prototype, will it fit to this? And this is a very important question. And I will show you what can be done here, or what we have done. So typically in these time critical systems, you have something which is called KPI, so key performance indicator. And this defines that at a certain point in the system lifetime or startup cycle, this has to be reached after a defined period of time. And what we can do here now is to relate these KPIs, these points in time, to external log files. So if we have a real system, we can run it, get a log file, and we will find some timestamps in there, and we want to compute them to this model. And this can be done by this markers. And what we have here is a regular expression which uses the regular expression language which comes with MPS. And then we have a tool which reads the external log file and finds this regular expression, extracts the timestamp, and compares it to this model. And what we see here is the reality is about 10.5 seconds for this key performance indicator, and our simulator is too fast. So either we have some regression in the real world software, or our simulator is too optimistic. We don't know, but this is an important information, and this will be done all the time for each sample, because we want to, with the simulator, we want to be ahead of the actual development, and this can only be done if all the parts of the model are correct. Okay, for the last couple of minutes, I will switch back to the presentation. And I have some more slides about some details behind the scenes. So here is a list of some examples we did for the Simbench applications, especially for this infotainment world. I won't go through this list. It's just some complex problems which you usually find in building these complex embedded products. Then I want to mention some challenges, and this is especially interesting regarding the presentation of results. So as you might imagine, the simulator provides a lot of data, and parts of this data we are currently lifting. These were all these yellow boxes with timings and also what we shown in the requirements and so on. But there's much more data. For example, the critical path of the system or the resource load over time, and all this is interesting, but you have to build a lot of UI and maybe new languages for representing the results, and we doing this with a slow pace. And one other problem with this lifting is that the mapping from the simulator results to the system model is not unique. So one thing which comes up for everyone who builds a component model is that the instant that a component might be instantiated several times, and then you have to know which of the instances you're looking at. And another similar problem is that if you have a behavior which runs multiple times, then you want to know which data you are looking at. You're looking at the 5th run or the 7th run and so on. And this makes the UI very complex to present all this to the user. You also, this is the last topic here, you want to compare multiple simulation runs, maybe change a feature and then look at multiple simulation runs side by side or do some algorithmic analysis. This is also, we built some tools in customer specific solutions for this, but there's no generic solution here. Okay, I think I will skip this one and go to the wrap up now. So what I have shown you during the last 45 minutes is a tool built with MPS, which can be used for modeling executable systems and doing simulations to find out timing, resource usage, and so on. And the important point in this presentation was this interactivity, that we can achieve a feeling like working with a spreadsheet. You choose something and you immediately get a reaction. And this supports this design space exploration, which systems engineers love. I also mentioned briefly the product line variability support and also the reporting of results to the user, where we still have to do some work to do this convincingly. There's a long list of ideas for the future. The first one I mentioned already. So we want to use incremental model transformations and map it on this intermediate language to be more flexible. And also there were some functionality extensions of the warp simulator which are not supported by the Simbench yet. And obviously, system engineers also would like to work in the browser, and so ModelX, this would be a good example for prototyping with ModelX. And I think I mentioned most of them. Maybe there are several domain-specific analysis possibilities like automatic optimization. So find the set of features which provides the most performant system, things like that. And many more ideas. Okay, we are not running out of work, but we're running out of time. So thanks for your attention.
Well, thank you, Klaus, for the talk. Very interesting. There are questions, but first a few comments. First of all, as suspected, darkness has indeed descended on Stuttgart as a consequence of your presentation.
Okay. Might be related to the time.
Yeah, possible. It's correlation. Possible. You never know, you know. The second thing, what I really like about I mean, I know Simbench. I've seen it before. But what I like is that it demonstrates how a modeling tool, and in particular MPS, can be used without any code generation or execution. Right? Lots of DSLs we've been building, we as ITEMIS, but also the community, are intended for running, for writing programs that run. You did something completely different, and I think it's very interesting to see that in action. All right. Before we come to the questions, I'd like to once again remind everybody to like the video if they enjoyed it. And now we get to the question. The first question is, as you can probably guess, by Federico. He says, maybe I missed I missed that part, but it's not clear to me how the warp works, how the system figures out which time to simulate.
Okay, yeah. I explained a little bit about the theory in the beginning, and warp will use this theory to find out the timings. So what it does is start at the beginning and then compute from all the resource needs it knows at this specific point in time. It computes the point in time, the next point in time where something changes, and then it warps to that point. And then it does the same again. And this iterates until it's running out of new events.
Okay. Sophia asks, if you're abstracting the simulation results at the model level, do you have any way of proof that this abstraction is correct? Or are there any experiment results to validate this? I think you got to that with your markers and log files, right?
Yeah, right. Yeah.
Okay.
So
this question was asked earlier.
Yeah.
So again, Federico, why did you use extend? Any particular reason?
Actually, there was an initial implementation of this warp simulator using C++, because we were thinking at the beginning that we have to be fast to do these quick cycles. But after all, it was a pain because we had to use the Java native interface. And so the choice was to switch to a different language, which is running on the JVM. And as I was fluent with extend at that time, I chose to use extend.
What would you choose today?
Probably Java in a later version.
Mm-hmm. I'm sure Federico is hoping for Kotlin.
Yeah. Right.
So Sophia again, which part of SysML of the SysML-like language was used for the domain?
Yeah, well, blocks and block parts and ports. So this would be the typical choice to represent the structural hierarchy.
Yeah, it's what everybody. It's the 5% of SysML that everybody uses.
Right. Yeah.
It's also, by the way, worth mentioning that we did build, just because we talked about systems engineering, we did build a prototype of SysML2 in MPS. It's not production ready, but if people are interested for some reason, ping us. It's an interesting combination of a standard like SysML and the ability to use MPS to extend that in domain-specific ways to build language abstractions on top of SysML, kind of like we did with Embedded and C. Anyway, it's just a diversion. Vladislav has kindly switched to non-Cyrillic fonts today, so I would have remembered the name, but anyway, thank you. So what's the point in simulating discrete resource consumptions? Is an exact solution not computable?
Well, so it's a good question. So what you could do is to have this kind of probabilities for all the values. Yeah. And there are actually simulators which can do this. So you put in probabilities, and what you get out are also probabilities.
So with probability, you mean a distribution of memory consumption?
Exactly.
Okay. Yeah.
Yeah. So this would be, maybe this already answered the question, but the question was also the exact solution. Yeah? And I think this is, on the one hand, it's difficult because if the simulation is doing several hundred steps with hundreds of components, then there's no closed formula for this. And also, if you're doing this in this early phase, you will not get 100% accurate result anyway, because all the numbers you put in, they are just estimates.
Yeah.
Or you extrapolated them from an earlier project or something like this. And so you get off the real value maybe 10% plus minus. And so it's no use of doing the exact computation there.
Yeah. And I think when we talked about this before, you said that the point of this tool is to give the engineer a way to estimate early in the design phase when there aren't any concrete numbers. But as the system evolves and concrete numbers are available, like actual memory that's been, welded into the hardware and stuff, then you would replace these estimates with actual measurements. And so over time, you're getting more and more representative of the actual system.
That's right. But there is a but.
Mm-hmm.
You have to abstract also from hardware properties, for example. So if you are modeling a hard disk, we are doing this by a couple of numbers right now, because benchmarks have shown that these couple of numbers is sufficient to achieve a certain accuracy. But if you want to bring in the latest knowledge of optimized hard disks, then this is not enough. You need a much better detailed model of this, and you will not build it in this kind of tool.
Yeah. Yeah. Another thing worth mentioning may be why you have chosen to do these rather rough estimates as opposed to do it more precisely is that you can run it fast to get this interactive user experience.
Yeah, exactly.
Julian is asking an interesting question. When the user input changes, e.g. you change the splash screen size, how does the simulation get updated immediately? I expect to have pressed the generate button in MPS each time.
Yes. So what we did there is to use a checking rule. So this is a technical solution. And the checking rule has a quick fix. And the quick fix runs the simulator and lifts the results. And then automatically MPS will update the editors. So we don't need any generation step, because this is done just by the Java code, which does the mapping to the simulator.
Yeah. Yeah, again, I think this is exactly why your talk is so interesting, because it does not execute programs in the classical sense. It doesn't generate, and it highlights that you can do things with models that are, that are different from pressing Control or Command F9 and generating a bunch of Java, which you then compile. So very, very nice. Sophia asks, how can you justify this DSL development as opposed to using SysML with simulation happening on Cameo Systems Modeler?
So we are using this, or this tool is used in a very early stage when you don't know all the details. And I don't know if Cameo Systems Modeler can do this, but usually the big commercial simulation tools, they will need some C code which is emulated on some emulated hardware. And this is not what we do here.
Also, I mean, the argument of building a DSL as opposed to using a big fat commercial tool is often that it's a tailor-made solution for a particular problem. It's more easily adaptable and so on. So there's lots of kind of non-functional trade-offs that are also worth considering. All right. So, and Sophia replies, yes, but it can be hard to learn it. And so, yeah, that's the general trade-off of a DSL. You get something more specific, but you might have to learn it. I mean,
and this is why I also had this little architecture diagram where I stated that we are building the DSL which the customer needs to model his systems. And it might be very SysML-ish, but it might be also different.
Yeah, it is not like everybody who builds systems is completely buying into using SysML. It's not like, maybe it will be like that in the future, but right now it's not like that. Okay, so we're out of questions. We have 4 more minutes. You might bring out your piano and play us a little bit a song, or should we continue with the next talk?
Better continue with the next talk, I guess.
All right. Thank you very much, Klaus.
Okay, my pleasure.